Do you have any questions before we begin?
I'll probably come up with some as we go through.
Okay, so start on page 75.
I apologize if I'm a little behind. I didn't watch Tuesday's lecture yet because I
Dude, it's a good lecture.
I had a test in thermo. And then I have dynamics homework and the lab, so it's been a little bit crazy this week.
Oh, I can't make this larger yet.
But that's okay, because we did specific heats in dynamics a little bit, so at least this will be kind of, I'll understand it.
So we talked the other day about specific heat at constant volume, right?
Mm-hmm.
Understand that. So let me get my pen. So when we say something like that, we are talking about, hold on. We're talking about CV. And so what I want to do is go from 3.39 to the next one. So CV is equal to, now how would you write this? Or how would you say this? What I find in a lot of students who are learning is that when they see this, they don't really know how to read this. They go CV equals dq dt when v is constant, which is fine, but what is this in the parentheses?
How the heat changes with time?
Not time.
Temperature?
Oh, temperature.
That should be temperature. It's a capital T. But
sorry, it looks like a lowercase t on your screen.
It's not how I mean, I know we'd say, how does the heat change with respect to temperature? I know that's how we'd say that. How does the heat change as the temperature goes up? But really, what I want you to think about in this equation here is that this is a fraction. So my other thing, what's fraction? What do you say when I say fraction? You guys remember? Comparison?
You go like that? That's a question?
Remember, I always said comparison. Whenever you hear that, you should think ratio, fraction. That's one of the things that I say, oh, always make sure you know this, right? So what I'm thinking about this as in the circle is that this is a ratio of dq. Now, what's dq?
The derivative of the heat.
The change of heat. The change in the quantity of heat.
I know that you want to say that, but that's not what it is.
Okay.
It's the amount of heat.
The specific amount, like the little amount, or just amount?
It is an amount. Now, because it's D, how much is it?
Little?
Infinitely small.
It's infinitely small, right? I mean, technically, that's what it is. But what I'm saying...
So implicitly, you're saying delta T, as in the Greek letter delta, referring to quantity when you say amount of heat.
Yeah, I mean, you could think of it as this, but the way that I want you to kind of perceive what this fraction is what is the ratio of the amount of heat to the observed temperature change? So when I say that CV is 717 joules per Kelvin per kilogram, even though they do it different, is I'm saying it's going to require 717 joules to raise the temperature 1 Kelvin for a kilogram of dry air. So this is, of course, for dry air. Okay, you understand what I'm saying? It's how much heat to get a Kelvin degree increase. It's the amount of, because that's what specific heat is defined as, is how much heat do you need to add to something to make the temperature go up by a degree. And I do that while I'm keeping the volume constant. And we said that Cp would be keeping the, I mean, it's the same thing, dT, when pressure is constant. It's the same thing. We just know that this value is going to be more. And really what they notice how in here, I want to point out to you, because I'm being inconsistent on purpose, is the unit is joules per kilogram per Kelvin. But I like the way that you think joules per Kelvin per kilogram, because it's the ratio of heat to a temperature change, a quantity of heat to causing the temperature to go up.
That's supposed to be 1,004 or 10,004.
Oh,
It's 1,004.
oh, that's not what I wanted.
And CV is 717. I don't know if you wrote that. Oh, okay, I see it now.
Yeah. Yeah, it's 1,004. Thanks, James. Okay. So if you look at 3.30, and then you look at the next one where it says CV is equal to du dt when the volume is constant. How is that? How do I go from dq dt to du dt?
Oh,
If the volume of the material is constant,
Yeah. Oh, you know what? I'm sorry, guys. This is 3.39. I read that wrong. So look at 3.38. What is 3.38?
dq equals du plus p d alpha.
Okay, that's the first law, right?
That's the first law. Okay.
Since alpha is a volume, and we're saying the volume stays the same, that second term goes away. So we're saying dq and du are the same. Right?
Okay, I see. I see what they're. Okay.
So
I see
if that's the case, then du is equal to cv dt. And we know that the volume's constant, so that's what we're saying. But in the first law, we now say dq equals cv dt plus p d alpha. And we have a much more important, for a lot of problem solving, form of the ideal gas law. Because we don't want to just deal with du. We want to deal with dt, because that's how we measure things. Right? And the other day I said that what is u? Just a reminder, James, you remember what u is?
I believe U was R was the dry air constant. No, what was U? I've got this written down somewhere, but I haven't gone over all
What's
my
u,
notes
anybody?
yesterday.
Internal energy change?
Well,
Or
not
just you?
just u is the internal energy.
Internal energy.
And I said
yeah.
to you that the internal energy is a function of temperature alone. So when the temperature changes, the internal energy, by its definition, is what's changing.
Okay, I remember that now.
Now, the majority of the internal energy, or in this case, we're going to say all of it, is going to be the kinetic energy of the molecules. There is some potential energy of the molecules if the molecules do what? You remember what we said? If the molecules do what?
If they're moving,
You know, if there's an affinity of the molecules toward each other, if there's attraction, if there's some chemical reactive properties of the molecules that you're putting in there, like I wouldn't want to just say that, oh, all gases are going to do this always. The point is air, the molecules of air are not reactive with each other for the great preponderance of stuff. So what we're saying is that the change in U, which is right under 3.41, so look at that equation. It doesn't matter how it goes. We talked about the path the other day. It's just going to be, if I want to know what that change in U is, it's going to be integrating CV dt. From temperature 1 to temperature 2, CV dt. But what do we know about CV? What do we know about CV? It's a what?
constant. So it can be pulled out.
Which means it's just that the change in U, which is U2 minus U1, the change in the internal energies of the gas from two different states is nothing more than CV times the change in the temperature. Okay? Do you see how that works? Or do you see what they're meaning by that?
Yeah.
Okay, so now let's go back to the first law. And we go dq equals CV dt plus P d alpha. Now something that as a memory tool, a mnemonic device for me to remember the different forms of the first law of thermodynamics is, notice this is P d alpha. So what's changing in this term? The volume, which means I'm going to use the CV, the constant volume one, in this term. And so if I do something a little bit different, you'll see, if I have the changing volume, I want one where the volume's the same. That's a mnemonic device. So I know that it's CV dt, so this V goes with the change over there. Now, the next one, if you go to 3.43, it's like, what the heck? So I'm just going to show you this because I'm nice and I like being nice to my students.
Yeah.
If I took the derivative of P alpha, right? And I want you to just remember that sometimes we said the ideal gas law was nRT. If I did it for a kilogram, then I'm specific volume. So I'm P alpha equals MRT or NRT, whichever one you want to use, right? So just keep in mind that this is the state of the gas, the pressure times the volume. We did the stuff yesterday or the other day with the volume pressure terms. I just want to remind you that. But since I'm taking the derivative of P alpha, do you agree that it's just going to be P d alpha plus alpha dP? Right? This is just taking the derivative. That's just a simple thing, right? That's the chain rule. James, you remember that James rule, or Jacob, you remember that?
Yes.
Okay, so what does P d alpha equal? Equals d P alpha minus alpha dP, right? That's just solving for this guy. Right? Does that make sense? I mean, I hope that makes sense to you. I'm not doing anything that's really that complicated. So what I do into here is I'm just going to go dq equals CV dt plus dp alpha minus alpha dp. I'm just plugging it in. Does that make sense?
Makes sense.
But what does p alpha equal?
nRT.
Well, in this case, right? Because if I did this one, PV equals MRT, and I said the kilograms are 1, then this becomes alpha. So it's just PV equals RT, or P alpha equals RT. Or if you preferred, you could have said P equals rho RT, and P alpha equals RT. That's why we're saying the inverse of density. So what that means, if that's the case, then this is dq equals CV dt plus the derivative of RT minus alpha dp. Right? I just substituted in here. But what's the derivative of a constant times a temperature?
Gradient?
No, the derivative of the constant is just plus the constant times dt
Oh,
Right.
sorry. I didn't-
minus alpha dp, which means it's dq equals cv plus r dt minus alpha dp. But we said the other day, and now we have, oh, that's, well, messy, I'm messy, I'm messy. We have an alternative form of the first law. Okay? Now, remember what I said earlier about, so you guys finished writing?
Yep.
Still writing.
So look at the screen. Remember I said this is constant volume, where the volume changes? Well, this is where the pressure changes, so that one's at constant pressure. You see how these two relate to each other? The only difference is this is a minus sign. But what I want you to remember is that the first law of thermodynamics in a qualitative form says what? That adding heat is going to cause a change in temperature plus work. And what is the work of a gas? The work of a gas is expansion, and that's an expansion. So that's where I know the plus is going to be there. So to me, and Allison, this is important for you too, it's like, I want you to know how to always think of the first law of thermodynamics.
I have a good practice problem, if you want to look at it, or I can say it for this exact thing. I just took it on my thermo test on Tuesday, and it's actually pretty similar to what we're doing. Let me find it.
Yeah, go ahead and say that.
It says, so the first part is consider a balloon containing 5 kilograms of dry air at 30 degrees Celsius. The balloon expands at constant pressure from 0.1 to 3.0 meters cubed. How much work is done by the balloon is part 1. And then the second part is, next the balloon is taken indoors where the air conditioning is set to 20 degrees Celsius. Over time, the balloon's temperature adjusts to match the indoor environment. Does the temperature of the balloon warm or cool to get to thermal equilibrium? And that part you have to use the constant pressure.
Yeah. So based on, anytime you deal with the problem, you have to say, okay, what are you given as constants?
Mm-hmm.
If I'm saying, well, what's work? And they give me constant pressure. Well, work is expansion. So if the gas doesn't expand, is it doing work?
Yeah, no, it's not doing work if it
Right?
doesn't.
It wouldn't be doing work if the gas doesn't expand, because that's your work term. So to do the work, if I know the change in volume, which you were given,
Yeah.
and I know the pressure, then I can tell you the work. Falls right out. Then if I'm doing one where I'm trying to figure out the amount of temperature change, it would be easy to deal with that, because in this case, do you understand that the pressure
It's constant, so it goes
is
away.
constant? So this term would go away, and then the heat and the temperature change are the same. So knowing, if you're going to put down a good set of notes, you need to have all the versions of the ideal gas law and all the versions of the first law of thermodynamics, so that makes sense. But again, in here, we sort of show why CV plus R is equal to CP.
And we can also prove that by plugging in the numbers, correct? By plugging in 717 plus.
That's what you did the other day. Now, on the very last thing before equation 3.46, then the paragraph before that, they talk about for ideal gases that are monatomic, the ratio of CP to CV to R is 5 to 3 to 2.
Wow, I've never seen this before. Is this a common thing, or is this just
this is like really important, but that's for monatomic.
Monatomic.
Single?
For diatomic, the ratio of CP to CV to R is 7 to 5 to 2.
Which makes sense.
So if you look at 1004 to 717 to 287, that's what you're getting.
Okay.
So why is dry air considered diatomic? Well, what's most of the atmosphere?
N2.
N2, O2.
Right? It's got a little bit of argon, so it makes it not exactly the same, but whatever.
H.
Right?
Okay.
So there's page 75. Any questions on that?
Sir.
And we're going to start doing some problems where you're going to be able to solve that. Okay, now let's go to this thing called enthalpy. Oh.
Oh, yeah.
Are you able to send me any of these problems so I can practice them as well?
Yeah, they're on a worksheet. So yes, I will send you that, Allison.
Thank you.
Enthalpy.
I think it's funny how close this is now to my thermo class, because
Thermo, yeah.
last class when we calculated the dry air molecular weight, that same night I had to do it in my thermo class, and we're about to do enthalpy today as well.
Is that taught out of your meteorology, atmospheric sciences department?
Yep.
Okay.
The lady who teaches it, I was going to do research with her this semester, but because of COVID, she wasn't able to allow in her laboratory or whatever, but she was actually a chemist.
That's where I learned my thermo is in chemistry.
Chemistry.
Yeah.
Actually, chemi. Is that an H, Paul?
Yeah, so this is small h.
Little h.
I will be neater for you. I will be so neat, in fact.
Yeah, Paul, I don't have the messiest handwriting right now. One of my friends says.
Oh, it does? Okay, that's cool. There we go. H. So now, again, notice what we have in here. We have this,
Okay.
which means what?
Just
Defines.
defined as.
So we're defining it, right? So there's nothing special about H being this, other than the fact is we're going to state what this is. And I'm interested that I use the word state because this deals with the state of the gas. PV equals nRT, right? That's the ideal gas law, which you know, I hope, by this point. This is known as the equation of state. So what are the state variables?
Pressure and temperature,
And
density.
you could say density, you could say V, right? Those are called state variables. So enthalpy is a measure of the state of a gas because what is U?
Internal energy.
Internal energy.
And the internal energy is a function only of temperature,
Yes.
pressure, and volume. So you multiply pressure and volume. So enthalpy is just a measure of the state of the gas. So if I add heat to this gas, add Q. Do you understand what am I going to do? I'm going to change the state. We know that if I add heat to a gas from the first law, I'm going to get warmer, which changes the internal energy, and I'm going to expand, which must change this. Even if it's a constant pressure, the volume's changing. I'm changing the state. So that we're saying is that the total heat that I give us is really just the change in the state of the gas. They put it this way. And really, you could make this delta H, whatever you want to do, right? Because that's what it is. You're saying if I add heat, some quantity of heat, I'm going to cause the gas to change its state by some state change. And that state change is called enthalpy. Do not confuse enthalpy with entropy.
Okay.
So enthalpy is just the change of the state.
Exactly. So, no. Say that again, James.
It's a measure to the change of the state.
No, enthalpy is the state. A change in enthalpy is a change of the state.
A change. Okay.
So what that tells me is if I take this and put it in derivative form, I'm saying that the change in enthalpy is going to be du plus dp alpha. Right? We know this. But it says, looking back at equation 3.4, so you look back at 3.4 and you say, okay, CV is D. So we know that du equals CV dt. So we go dH equals CV dt plus dP alpha. Right? Because that's 3.4. And combined with 3.43. Well, what's 3.43? dQ equals CV dt. I'm just going to write it down. Equals CV dt plus dP alpha minus alpha dp. And since I'm using color, which, you know, makes me happy, because I think sometimes this color stuff works. Do you understand that CVDT minus dp alpha is right here? They're the same. So what that tells me I can do is dq equals dh minus alpha dp. Which is what we wanted to get to. But by comparing that to equation 3.46, so again, turn the page back, which was the first law that we just stated in the last one, we see that H must equal to Cp dt.
Bless you.
Thank you.
I'm sorry. dH equals Cp dt.
Mhm.
And then, of course, what I can do is just, instead of taking the derivative form, I just say that the actual state is Cp times T. So if I, and again, do you understand all I've really done? This is the derivative form. I'm going to integrate. I'm going to sum up an infinite number of these, and I get, well, here, let me show you what I do. From H1 to H0, or sorry,
No.
to H2, and I'm doing from T1 to T2, whatever, right? And I'm saying that when I start, if I start at the beginning and I call this absolute zero, then what's the enthalpy when I'm at absolute zero?
0.
Why is that? If the gas is at absolute zero, what's the internal energy?
Zero.
Nothing.
There is
Zero.
no.
And a gas that's at absolute zero, and if you go into the mechanical universe and you can look at the next set of information, absolute zero would mean that the gas has no pressure and no volume. So it's like a limit. You can't get there. So we're just saying that whatever this value is, H2, T2, you're just saying H is CPT. So I'm saying if I told you I have air that's at 283 Kelvin, what is the enthalpy of the air at 283 Kelvin? I would just take 1,004 times 283, and that gives me something called enthalpy. That's it. And you could sit there and go, well, I'm not really sure what enthalpy is. And the point is, you don't need to know that at this point. You don't need to understand that. You just need to know there's a state of the gas. And because of the first law and all the derivations, we're saying that the state of the gas, which is internal plus the state in terms of pressure and volume, is nothing more than the specific heat at constant pressure times the temperature. So let's take a look at the very last paragraph on 76. Bruce, would you read that out loud? I'm tired of my voice.
Hence, if the material is partial, this one, right?
So when a layer on 76, bottom left.
Oh, bottom left. When a layer of air that is at rest in hydrostatic balance is heated, for example, by radiative transfer, the weight of the overlying air pressing down on it remains constant. Hence, the heating is at a constant pressure. The energy added to the air is realized in the form of an increase in enthalpy, or sensible heat, as the atmospheric scientists commonly refer to it, N dq equals dH equals Cp dt.
So in other words, what you're saying is at this point, you've got a layer of air, let's say the boundary layer, and there's atmosphere pushing down the boundary layer, but I have heating going on. I'm heating the boundary layer. What I'm going to do is I'm going to expand that atmosphere, right? But it's still at constant pressure because the weight of the air above you is still the same.
Mm-hmm.
If it's in hydrostatic.
So that implies the expansion goes sideways.
It implies the expansion goes up.
Oh.
Because now here is something interesting. It says the air within the layer expands as it warms, doing work on the overlying air by lifting against the Earth's gravitational attraction. Of the energy per unit mass imparted to the air by heating, we see that du is CVDT is reflected an increase in internal energy, and PD alpha equals RDT is expended during doing work on the overlying air.
So this is describing buoyancy?
This is describing how the low atmosphere, or any layer of the atmosphere, is changing. Now, I want you to take a look at a problem in the book. (3.28). And this is one of the ones that I need to assign you, but I want you to do this.
It's page 103.
Thank you.
On page 103. Yeah, I'm sorry, page 103. So it's an exercise at the end of the chapter. That's a problem I want you to solve. But here's the problem. I'm giving you a heat source, and the layer is going to expand. 1,000 to 500 millibar layer is going to expand. Do you understand that that expansion is actually doing work on top of the 500 millibars? You're pushing that layer up higher. You're expanding the atmosphere. In order to solve that problem, the way they've given it to you, you have to assume the work is zero. It says, apart from the slight vertical motion associated with the expansion of the air. And that's going to calculate the temperature. And so in other words, you're heating the air, right? Just like the ground might heat the earth, or there might atmosphere heating the earth. It's a layer of sensible heat. In order to, you have to use the first law. And in order to use the first law, you have to assume the work term is zero, which it's not. But you have to assume that, or else you can't solve the problem with the information they give you. That when I first was teaching this class and I was working out all the problems, I spent 19 hours on this one problem.
Oh, so that's the one you give us. Great.
Mm-hmm. But the reason I spent 19 hours on it is I assumed that it was doing work. If you assume that it doesn't work, it takes a few minutes. So I was like, are you kidding me?
Someone who spent 19 hours on it already.
We had a visiting physicist from Czechoslovakia at the time, the Czech Republic, and he was working on it with me, and we could not come up with an answer. We realized it's because the work term is zero. But clearly on page 76, they go, it takes work because you're lifting the atmosphere. So that's not going to help us.
So is there a reason why it's zero? Like, does the problem kind of hint at that, or?
No, it's just because based on the information they give you, you're not supposed to calculate that other thing.
Okay.
So look over here. Because the Earth's atmosphere is made up mainly of diatomic acids, the energy added by the heating is partitioned, keyword, between the increase in internal energy and the expansion work P d alpha in the ratio of 5 to 2. So imagine that I have this. I'm going to go ahead and erase this because I don't need to have it. And I said, I add heat to a gas. And it's going to do work plus change in temperature. If I have 7 joules of heat, 5 of them will do, whoops, hold on, let me do this. Just for the sake of this problem, I'm going to rewrite it differently. That's the way it's going to work. So 5 of the 7 joules of heat that you give the air will cause a temperature increase. 2 of them will cause a work increase. Huh.
So effectively,
I'm wondering if that problem that I just assigned to you, I'm wondering if maybe if I had used this information, I could have solved it.
Can you do it? I want to see it.
So effectively, what you were saying here is that we just have to apply the ratio to the formula, and we get something like this, and we can solve for all aspects of it.
Well, no, you don't need to do that in the problem to solve it to get the answer the book's looking for. But I'm wondering if this would work. Huh. Anyway, it's just one of those things where how much heat goes into making the temperature warmer and how much heat goes into expansion. And there's a set number. Now,
Is that a coincidence that those numbers are the same as the ratio of CP, CV, and R?
no, that's all falling out because of the way that those terms are falling out of the first law. That ratio that you get is the reason for this.
And if it was monotonic, it'd be 532.
532, right? But since air is primarily diatomic.
Diatomic, yes.
So pretty interesting, isn't it?
So
Here's the last paragraph. Pretty much is we're going to write a more general expression that's applicable to a moving air parcel. The pressure which changes as it rises or sinks relative to surrounding air, right? We're moving a parcel through the atmosphere. By combining 320, 340, and 348 and 350. So let's do that. And this is the way that, if you're going to be a good student, a smart student, you need to do stuff like this. So first thing is, what's 320? Give me the equation.
If water vapor
No, equation 320, page 68.
Oh, wow.
D of geopotential is defined as G dz, which is equal to minus alpha dp.
Okay? The change in the geopotential, d phi, capital phi, is equal to minus alpha dp. All right, then 348. So if in your notes, you should say 3.20. Because if you have a good set of notes, you want to kind of reference, well, where did this come from? Oh, we did this before. And then it says 3.48 dq equals dH minus alpha dP. And then 3.5 is H equals CP dt. No, I'm sorry, CPT. And I want to combine all of these things. Well, where do I do it first? It seems like I'm going to put this in here. So that's going to lead me to dq equals dH plus d phi.
I think you mean, instead of 3.5, you mean 350.
3.5, yeah, 350. But I can also write that as this. But what does H equal? You guys ready for something really cool? Because this is where life kind of gets really cool. In an adiabatic process, 0 equals dq, which means dCpt plus that must equal 0, right? If the change in heat, if dq, the amount of, really the better way, how much heat am I applying? It's 0, then the change of these two terms together must be 0, which means that this must be, oops, not 0, constant.
So okay, I see. So you integrate that, and what's the?
Not integrated. I'm saying if this is 0, then this right side must be 0. You're looking at the change in this. Well, the change in what is 0? The change in the constant.
Constant.
So just what's in there.
And the derivative of constant is 0. That's where I'm going.
Right? But Cp over T plus this, which really is GdZ, is a constant. So if I go higher, what does the temperature have to do?
That's to kind of
Go ahead, Nick. This is a teeter-totter.
so it kind of just has to balance itself out.
Right? And who's staying the same?
It's inversely proportional.
Staying the same. So if this goes up,
Temperature goes down.
temperature goes down. Well, sounds like that might be important. Do you think?
Yep.
Well, it's what happens in real life. So
That sounds like something we talked about just on Tuesday.
So now I'm going to jump ahead, and I want to keep, I'm going to go back to the other stuff and read it, but I want to jump ahead to 3.4.2 on page 77, because that's the continuation of this. So I'm going to take this information, and I'm going to say, I'm going to take this and divide through I'm going to go back to this one. That's what they're doing here. So I'm going to take this equation oops, sorry. Ah, damn it. Sometimes I'm not good with Epic Pen. I'm not precise enough. I'm going to take, see, I don't want to do that, damn it. This is what I want to do. I'm going to go up to here. And I'm going to go, all right, I'm going to take this information, and I'm going to go dCp T plus G, I'm sorry, dz. Equals 0. But do you agree that that's just Cp dt plus hold on. I made a mistake in here, okay? So when I go back to 320, so go back over here for a second. What does d phi equal besides this? It's also g dz, okay? So what I want to do is when I go over here, this is not the derivative of all of those, so I'm going to erase this. I'm going to say,
Whoa.
I'm going to say this. This is not, it's d phi, so it's d of Cp dt plus d phi, but d phi is g dz, so I don't have the, so I don't want the d in front of this stuff. Now I get this plus g dz equals 0. Divide through by dz. I get Cp dt dz equals, or I'm sorry, plus g equals 0. Then I'm going to go Cp, I'll do it step by step, dz equals minus g dt dz equals minus g over Cp, but gamma sub d is negative dt dz, right? Because remember we did this with lapse rates many times. We said that the change in temperature with height, the value inside here is negative, and a negative negative is a positive lapse rate. Must be equal to g over Cp.
What's the subscript on gamma? Down.
Because why is it equal to 0? It's an adiabatic process.
Oh, so you're implying that's, okay.
So
Right, so we've implied that it's 0 in an adiabatic process, which is over here. So what you need to do is take out your calculator and calculate, calculate
Okay.
G over Cp, which is 9.81 meters per second squared divided by 1004 joules per degree per kilogram, or joules per kilogram per degree. What's the number you get?
Uh, 0.00977.
977?
Yeah.
E1 minus third.
What's the unit going to be? right? You got a joule. You gotta know what a joule is.
Yeah, it's a Newton meter, and Newton is kilogram meter per second squared.
So do you understand I have a kilogram and a per kilogram? They go away.
Yeah.
The negative kelvins go up on top.
Yep.
I have a meter per second squared in the top and the bottom. So this should be
Kelvin per meter.
Kelvin per meter. Because this is a Newton meter. And a Newton's got a meter in it, so that goes away, but the extra meter. So I don't want that. I want to multiply by 1,000 to get to kilometers. And that's the dry adiabatic lapse rate, 9.77 K per kilometer, degrees per kilometer. So we've always said this, but really it's 9.77.
All right, so that's gamma D.
Dry adiabatic lapse rate. What are you
Okay.
asking gamma D? What do you think that is?
I just want to make sure I'm reading the subscript right.
Ah.
With respect to signs, is that supposed to be a negative or is that supposed to be a positive when you talk about lapse rates?
Okay, so over here, a lapse rate is a rate of getting colder. It's getting colder by 9.77. Because we define a lapse rate, and this is what's going on down here, Bruce. We're defining the lapse rate to be the negative change in temperature. So, right, dT/dz,
That's a question.
That's a question.
how does the temperature change with height? When it's going up, you're getting colder. So the value inside the parentheses is negative. A negative negative is a positive lapse rate. But the lapse rate is G over Cp, which is just the numbers. And now we've derived what the dry adiabatic lapse rate is from the first law of thermodynamics. And so we know that when there's a pressure change, you are going to drop the temperature, even though there's no heat process in it. So now in the first law, when I go heat in equals work plus a change in the temperature, and there's no heat, then the work is which is expansion, is the change in temperature. But so what would cause the dry adiabatic lapse rate to change?
If it's not 80, oh, well, hold on.
I mean, how about if you said if the air wasn't diatomic?
Yeah, if it was wet.
No, if it wasn't diatomic. Now, when you put water vapor in the air, you are going to change some of these slightly. But I don't think they worry about that. So now we go back to the adiabatic process, and I want you to read through this stuff, not now, but certainly before the next class. I think this is important that you understand it. But I want you to look at figure 6.35. Can I erase this? Do you have any questions on this?
No, I took a picture.
Everybody good?
Good.
Roger.
Kind of cool, isn't it?
Mhm.
Isn't meteorology a cool science?
Yes, it is.
It's fancy.
I love it.
Hot.
I have a love-hate relationship with it. Let's just put it at that.
What I like about it is that it's, and I'm telling you, you guys don't know how ignorant people are about what meteorology is. Do you know how many times I fight with some of the engineers here because they think meteorology is just about TV? I'm
I
like,
know.
dude, it's an applied physics degree.
No, my whole thing is when I was taking Calc 3 or DiffEQ at COD, and they'd always ask me the famous question of, are you sure you have to take this class? No, I'm just taking this because I enjoy pain and torture and calculus.
It's amazing how little they know about what meteorologists do. And engineers, mathematicians, physicists, they all think it's kind of weird. I'm like, dude, we take as much math as you, we take as much physics as you, and then a whole lot more.
The head physicist at this school was in the atmospheric science department before she moved full-time back to physics, but she wrote the textbook for thermodynamics. And
I'm telling you, it's an amazing field. We are way more advanced than other people know that, because they think it's just TV stuff, and that drives me crazy. I really hate that. Anyway, so we have in here, we have a diagram that looks like this, and another one that goes like this.
That's supposed to be a straight line?
No, they're it's figured out 3.5. So this is A to C to B. And this is an adiabat. And this is an isotherm. And this is pressure and volume. And I want to point out to you something of utmost importance. What is the area underneath the curve?
The integration?
It's the integration of what, James?
The integration of B to A.
Oh, that's the limits.
But no. What am I integrating? What does integration mean?
You're summing up a bunch of infinite little slices to get.
Oh, bad.
I'm summing up an infinite number of infinitely small, and I would say little rectangles, right? Little rectangles. Do you agree? And I add them all together, and then that becomes the area underneath this curve. But what is the area underneath the adiabat? What is the area underneath the adiabat? Same thing.
Yeah. When you say same thing, are you saying equivalent?
No. I mean,
Okay.
yeah, good question. Sorry. It is the same thing in terms of its area underneath the curve.
Right.
But the area is P dV, which is what?
Okay.
So which one, if I'm going to expand, let me do it this way. Let's go, I'm going to compress the gas. So I'm going from A to B. Now let's go A to B, or A to C. It takes work to compress a gas. Do you agree?
Yes.
Which is going to require more work? Which of these two diagrams is more work?
I want to say B to A because it looks like there's a lot more of a wides.
Okay. Hold on. What I should do is this. Oops. should go all the way to here. C and B should end up at the same volume. I should have done this better so that this becomes the same point, which has more area underneath the curve.
C to A.
Okay, more area, more work. Less area, less work. So in other words, if I'm compressing a gas from some volume to another volume, from V1 to V2, which requires more effort, to compress it adiabatically or to compress it isothermally?
Radically.
An adiabatic compression will require more work. Listen to what I just said. An adiabatic compression requires more work. Can you explain why that is? Why you know, in a qualitative standpoint, why do you think that is? Imagine that I take a piston and I go down, I push the piston down.
The pressure is going to increase.
The pressure will go up, which it does, right? But what else would go up if I compress the air?
Temperature.
Temperature.
So how do I do it isothermally? What do I have to do?
You have to remove temperature, remove heat.
Remove the
I
heat.
have to remove heat, which means I need to put it on something that's making it what?
Cooler.
Colder.
Colder.
If I put it on something that's making it colder, do you understand that the molecules will give me less resistance?
Yes.
Mm-hmm.
So it doesn't take as much work to do that when I'm cooling it. We're going to put this together when we make an engine, because we have adiabatic and isothermal components of the engine. And it's because of that that we get work, that engines can do work. And we'll be talking about efficiency and all that other stuff. So that's really cool. Okay, now, read the rest of this done. I wanted to show this to you because we're going to come back to it when we deal with the engine and what's known as the Carnot engine, the Carnot cycle, which is awesome also. Everything in this section I like a lot. All right, now we're going to define potential temperature. So this, mon frère, is the derivation of Poisson's equation.
It's your favorite.
It is my favorite.
What page is this on?
This is page 78. Okay, so this is what, and I'm telling you, students with low math backgrounds have been successful on this because this will test you out to see how much you actually know about calculus and equations and manipulations and logs and everything. So love, love, love this. We start out by saying dq equals Cp dt minus alpha dp. Again, pressure is constant in this term, which means it changes in this term. So we are using this form of what? What is this? And you should write this here. That's the first law of thermodynamics. Since Poisson's equation is going to define potential temperature, which in my classes, I think you all know what potential temperature is. The temperature to which an air would be if brought dry adiabatically to 1,000 millibars. We know that in a potential temperature, this term goes to 0 is our first statement. And then we say Cp dt equals alpha dP. But if I look at something like this, and it's pretty straightforward, do you agree that I could integrate the left side pretty easily?
Yeah.
Can I integrate the right side?
No, because alpha depends on pressure,
P.
right?
No, because alpha depends on pressure. But I know that P alpha equals RT, right? I know that. That's the ideal gas law. So I'm going to go Cp dt equals equals RT over P dP. And I'm going to isolate dP over P. And that will put Cp over R dt over T on that side of the equation.
I love differential equations when they do the separable integrals. I'm such a nerd, but this is like my favorite.
I know, it's really cool. It's like, you know what it is? It's clever, and you're like, cool. I like clever things, and I think the brain likes clever things.
Diffie Cube was
Yeah.
the math class that I actually enjoyed because it wasn't anything new. It was just using everything that you've learned and then putting it together.
I totally agree with you. I think differential equations so far more fun than all of the other calc.
I liked it too. Just I kind of had a crappy professor, but
I took it when I was in college, and I actually had a great professor.
I had a great professor. She was awesome.
Then I took it at COD. When I came back teaching here, I needed to take a refresher, so I took Diffie Q, and my teacher was so anal and so precise on everything. It was awesome. And
Math classes are inherently hard when they're taught by professional mathematicians.
Yeah, it was, well, my scores on my test were 93, 98, 99, and 100. I finally got a perfect score on the test because I kept making stupid little mistakes. Okay,
Yep.
so over here, I want to integrate. Do you agree that now I can integrate?
Yes.
mhm.
So the integration on the left is pretty quick. What will the integral of dP over P be?
Ln.
Log P plus C.
Remember how we said that's one of the ones that you really need to know. And over here, I'm going to put the integration sign there.
It'll be the same thing.
It's the same thing, the natural log. And Cp over R is those are constants, so I can keep that outside. I'm like, wow, that's a really easy integral. However, before I do that integration,
We're going to do the bounds.
I need to know the limits of integration. Because this is really the tricky part. So what I'm saying is this. I'm taking it from one pressure to another pressure. Well, where am I taking it to?
1,000 millibars.
So
Aren't you
I'm going to
taking
take
it
it
from
from
the surface?
whatever pressure to P naught, which we'll say is 1,000 millibars. So whatever pressure to 1,000 millibars. Now, what's the temperature at some pressure?
Theta 1.
No. I'm taking an air. Let's say I give you a problem and I say, hey, take a parcel of air, 500 millibars and its temperature is negative 12. What's theta? Right? You take a dry adiabatic to 1,000 millibars, right? So the temperature here is just some value T, whatever that T is. And I want to point out to you that this corresponds to that. It's temperature T at pressure P. Okay, well, what will the temperature be at 1,000 millibars?
You not?
No. If I bring the box adiabatically to 1,000 millibars, what's the temperature? It
That's the
becomes,
potential temperature, the theta.
Right
it
back.
becomes theta. So I'm defining theta, not sorry,
You're saying theta E?
no, I
Yeah.
have it. I'm defining theta to be the temperature at 1,000 millibars. So that's the tricky part, is the limits of integration. Now, the easy part is I can just integrate it. So I get Cp over R natural log of T from
Do you want us to plug in 1,000 or do you want us to keep it as P naught?
as long as you know that P naught is 1,000, you keep it as P naught.
Aren't the limits flipped, or based on what it says in the book?
Okay. Nick asked a question, interesting question. He says, well, based on what it says in the book, aren't the limits flipped?
It depends where we're going.
If I flip the limits over here, I flip the limits over there,
Mm-hmm.
and what would the difference be?
Nothing.
If I flip
Yeah.
limits with any integration, what am I really doing? So I want to show you something. If I go from,
Yeah.
if I integrate this from 30 to 35, isn't that going to be T evaluated from 35 to 30, which is equal to 35 minus 30, which is equal to 5, right?
Mm-hmm. Yeah.
Flip them. So rather than rewriting the whole thing, how if I just did this?
Be -5.
So when I flip integrations, what do? It's a negative sign. But if
Yeah.
I'm flipping them on both sides, what does the negative sign do?
Disappears.
It's also going to be negative on the
They
other side,
cancel
so
out.
it
So
doesn't
it
matter.
doesn't matter, right?
Yeah.
I
Yeah.
think this way is better because I want to say I'm taking a parcel from some pressure to 1,000 millibars, from here to there.
Okay, that makes sense. Yeah.
But those are good questions, right? Because you need to understand what flipping limits does. Is it just reverses the order of operations, 35 minus 30, as opposed to 30 minus 35.
Okay. I just wondered why you had them flipped compared to the book. So, but it makes
Exactly.
sense.
Okay, and that's why it's a good question. Okay, so what do I got? What do I got here? I go Cp over R is the natural log of theta minus the natural log of T equals P naught minus P.
Natural log.
Natural log of P naught minus the natural log of P. Now you could sit there and go, oh, what am I trying to do? Let's define what I'm trying to do. What do I want to define?
Theta.
I want to define theta. So if I'm defining theta, I need to isolate theta. But I don't like dealing with natural logs of theta.
So take the exponential to each side.
Well, not yet.
Not
Let's
yet.
make something simpler. Do I like differences in natural logs?
Yes.
No, divide them.
No, right. You want ratios.
I can do this. So that's something I can do, right? And again, you're defining rules of logs, right? That's what you're using. You're not defining, but you're using a rule of logs. Now, there's another rule of log to make this side a little bit different.
Oh yeah, that one.
Right.
Now I take the analog of both sides. Or if you want to look at that, I'm taking E to that side equals E to that side. And those are the analogs. You're taking the exponential. And what that allows you to do is you just go theta over T to the CP over R equals P naught over P. And now what do?
The exponent to the other side.
I can take both sides to R over CP. Sorry, I'm running out of real estate. Do you understand what I've done here? I've taken both sides to the R over CP power.
Yes.
Because if I take x squared and I take it to the negative 1/2, I'm sorry. If I take it to the 1/2 power, don't I multiply exponents, which is just equal to x? So I'm taking it to the inverse of that, R over CP. So this becomes R over CP. And then theta equals T times P naught over P, parentheses, to the R over CP.
I guess at the end of the day, with those limits, it just saved time for taking the reciprocal of 1 over theta, which eventually you would get.
Exactly. I could do a lot of things, right? And here's the point, Nick. And by the way, did I give you my virtual temperature correction document?
No.
You know what I found out yesterday? I posted it to my 11:15 class, not you guys.
Oops.
So I will take care of that today. Later on, I will give you that document so you have it. I think we already went through it, but I think I posted it. So I have theta right now. And what I would do if I were you is take it many different ways. You could put the CP over DT on a different side. I don't care which one you do. Practice it in different ways, and then you'll always come to the same answer if you do your rules of mathematics correctly. That's the great thing about math. If you follow the rules, you will get the same answer. If you break the rules, you will get different answers. So I get theta equals T times P naught over P to the R over CP, but we're going to use RD over CP, which is 287 over 1004 joules per Kelvin per kilogram, joules per Kelvin per kilogram. They all go away. So what is 287 divided by 1004? If you do it, it's 0.286. So what I can do then is give you a problem. I said temperature is negative 12 degrees Celsius pressure is 500 millibars. What's theta? Go ahead and calculate that. What do you get? You get that?
No.
Did you convert the
Yes.
temperature from Celsius to Kelvin?
Of course.
No, I was saying because someone said no. So I was
You
just.
have to put it in Kelvin.
You got to go Kelvin, yeah.
Do you have to put it in hectopascals?
No,
Why not?
because the units drop out no matter what
Right.
you put.
It's a ratio, right? The units are going to go away. So it's the ratios. You don't have to worry about it.
Oh, there it is. I got it. Okay.
So once you get to this stage, it's just plug and chug, huh?
Yeah, and 1,000 divided by 500 is 2. So it's 2 to the 0.286 times 261, 318.2 Kelvin. How easy is that?
It's actually really easy once it's down to the point where it's just you can just put numbers in. It wasn't even that hard to get there. It's probably the easiest thing I've seen so far.
Right, that's what I'm saying. Even students with a relatively limited background, there's not a lot in here. When you go back, the only calculus you have to deal with is the natural log of P over P dP. That's what you're integrating. I'm sorry, well, no, what am I saying? Hello, let's try that again.
P over P.
You're doing this. Oops. You're integrating dP over P, which is nothing more than the natural log of P. And I said that was super important. And we'll see that a lot of times in this class. By the way, guess what this is all about solving for theta. So for theta, we solved how to do that, Poisson's equation. We figured out how to determine the dry adiabatic lapse rate, which is really only just this. That's pretty straightforward. When we do this is hard. Solving for theta E, the deriving theta E, that's going to be difficult. Okay,
That's environmental.
So that's the equivalent potential temperature.
Oh,
Yeah, that becomes really a pain in the ass. Very interesting, and it's actually very fun, but it is hard. Okay,
That was Poisson's equation there, is what we just did.
what'd you say?
That was the Poisson's equation.
Poisson, say Poisson.
Poisson.
Like croissant.
Poisson's equation.
So that's Poisson's equation. Now, a couple things I want to go through with you. First of all, I want you to have read all of this stuff on thermodynamic diagrams. And they talk about it being a pseudo-adiabatic. It talks about So skew T log P, which the ordinate of that diagram, rather than being pressure. So look at figure 3.6. What kind of a diagram is that? And you have pressure versus type. So 3.6
Pressure versus type?
versus temperature, sorry.
Oh.
Sometimes I think ahead of my mouth.
Temperature versus pressure.
Yeah, so 3.5 is that's called a Stuba. And what is that blue area?
In 3.6?
Yeah, that blue area is what my thermodynamic diagrams are. So what do we say when we define that? We say all the dry adiabats are parallel, but are they really parallel? They can't be.
They can't be if they.
They all go to the same point. And what point do they go to? When the pressure is zero, the temperature is 0 Kelvin. So they all have to go to that point. It's just in the domain of the chart, which is the blue area, they look like they're parallel, but they're not. So that would be the Stuba diagram. Now, 3.7 is called a skew T.
3.6 is the Stuba as well?
3.6 is the Stuba. 3.7 is the skew T. Skew T log P. So rather than going pressure and temperature, which is this guy, they do log P and temperature. And the temperatures get skewed. So isotherms run this way, not up and down. The advantage is that the difference between an isotherm and a dry adiabat, and I think we've talked about this, is about 90 degrees.
And your
But
preference?
what do the dry adiabats do? They curve.
Your preference is for Stuba?
No, skew T is much more reasonable for doing calculations, but for teaching, the Stuba is far easier.
Got it.
Because I just can't get people to think
skewed.
Stuva is a fun word to say.
Stufe.
Stuva, auf Deutsch.
Right. Now,
This whole Stuve?
the other thing that you want to have is you want to do page 80 and go all the way to 84. That one you should be able to read through and understand it pretty well, although we need to do something about saturation mixing ratio, so we'll work on that next week. I would also like you, so I'd like you to study through page 84 for Tuesday. And then 3.5.4 and 3.5.5, the theta E.
Sorry, I didn't catch that.
So look at page 85.
Got it.
I want you to read all of the section, all the way up to static stability, all the way to 3.6. I want you to read all of that. I want you to study the first part, because this stuff on page 85, don't spend a lot of time on it, but read it and see if you can. I mean, why not? Because then we can do it in class. You'll have maybe a better appreciation for it.
Yes, please, because I want to do static stability because we just started that in dynamics, and I need you to explain it to me.
So we will be doing static stability next week. So we're going to do theta E and static stability this coming up.
Can you do static stability on Thursday so I can sit in and answer real time again?
Next Thursday? Yeah, we'll be there by next Thursday. You can't make Tuesdays, or are you going to be here on Tuesday?
So I have soil science lab on Tuesdays, the exact time, so that's why I listen to the lectures afterwards.
Okay. Oops. The lecture yesterday was good.
Yeah, I was just finishing up listening to last Tuesday's lecture, and I didn't have time.
Okay. So we'll be doing a lot of that stuff, and then, so the way it looks like is we'll do a test after this entire unit. Because you're online, I mean, look, here's what I'm thinking. I could give you a test where you have to study for it and you just take the test. And I would trust you that you are going to be honest with it. Or I could give you a take-home test and give you an extended time to work it up and come up with notes. What do you think would serve you better?
Take home, please.
Work up.
Ooh.
Jim, what did you say?
I said work up. The second one.
Okay. What do the rest
Take
of you
home.
guys think?
I say take home because then I can work on it also, and I end up learning more because I do the problems on like a whiteboard versus rushing through it for a test.
That does make sense.
Here's the thing. If you were a normal intermediate class where I scream and shout at people, I would have given you the test. But because you guys are actually here all the time and you're really good, and I think you're actually doing well, and I'm getting good interaction with you, everybody except Jacob, who's always hiding.
Don't worry though. I'll have my camera back next week. I'm just
Well,
still taking off
it's
my
kind of nice.
allergy.
I hear your voice, but I don't have to see your face, which always makes me happy.
Oh.
Ooh. Wow.
But you guys are doing well, so I think I'm going to make it a take-home, and I'm just going to do midterm final is the way I feel about it.
Okay.
But the last thing I want to do with you guys today, just to kind of talk about.
Can we go over 319?
Oh, also, is there going to be a decent like study guide or something, or are we going to have to collaborate to make?
You already have that.
Yeah, Paul doesn't make study guides ever.
Not
All
for
right.
this. You have it. You have this.
Unit 2.
You have Unit 2 worksheet. Oops.
Okay, so all the worksheets are just pretty much what we need. Gotcha.
Yeah. Did you watch these?
Yes.
Okay. So the last two we'll do later. You don't have to do this, but I like them. They're really interesting to me. So.
He's a good lecturer.
Oh, he's amazing. Oh, it opened. So when you go into here, they have all this stuff with virtual temperature, blah, 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 hydrostatics in here, geopotential, and then there's problems embedded within this that you should be doing. So Allison, I'll send you this. First law of thermodynamics. We're already here through specific heats, enthalpy. Here's this diagram we talked about today, and here's Poisson's equation. So what I think a good thing for you to do for next week is to go through Poisson's equation and then just write what I'm doing in each of these steps, because I think it's a little bit different. Because here I went from theta to t and from p naught to p, like the book does. And maybe that's better for you to practice manipulation of equations. And then we're going to get into latent heats coming up. So there's a lot of problems in the book. These are the ones that you're going to be needing to start working on.
Are you going to be doing any of these so that I can?
Yeah, I will do that, but you got to do them first. Because if I solve the problems for you without you struggling through that, then I'm taking away your greatest tool, which is effort. So Jim, what did you ask about?
You assigned 319 for today. I was just wondering if you were going to go over it.
What did you come up with? Oh, just the molecular weight of Venus?
Well, there was two answers. One was the apparent weight, and the other one was the gas constant.
Okay, did everybody else do that?
I did.
What did you get as the apparent weight?
Am I in the right thing?
I got 43.2 grams per mole.
43.2, that seems right.
Yeah, I got the same thing.
And then what's your ideal gas constant?
192.5 joules per Kelvin kilogram.
Yep.
So what would the dry adiabatic lapse rate be? Well, what is
Well,
the atmosphere of Venus? It's primarily what?
it's CO2.
Right? So it's mostly CO2. So you would have to figure out, you already know what the ideal gas constant is. Then you'd have to look at the specific heat for carbon dioxide, which I'm not sure I know what that is offhand.
Look it up in CRC.
So you could do that. You could figure out what it is. You'd also have to know the gravity. You'd have to know gravity
Gravity.
on
Venus.
Venus. So that's kind of interesting. But yeah, that was a pretty straightforward problem. But here's all the problems you're going to be working. So I'll send you that after class, Allison, okay?
Thank you.
And then you should have this whole worksheet filled out because I'm going to ask you, for the take-home test, I'm going to ask you problems that you need to solve. Okay? And the take-home test, I'll give you about a week to do it. So it'll be long because it's a midterm.
Can you do it before the October 5th week?
No.
Dang it. I wanted to use it as a study tool to study for my dynamics.
Well, you can put all the stuff together to study for it anyway.
Yeah.
Okay, guys, that should end our session today. I will see you guys next week. Have a great weekend. Good weather. Have fun. Mike, you going to be flying or are you going to be around next week or what's up?
Yeah.
You'll be here? Okay. Awesome. Any questions before we go?
Yeah, read the static stability, and then we do the worksheet through Frenchman's equations.
Read through up to static stability. You don't need to study that yet. You can read that next
Okay.
week. But try to get that stuff. Okay, guys. I will see you all later.
Yeah.
All right.
Later.
Have a good weekend, everyone. Bye-bye.